All right, now we move to the last chapter of this whole semester. We will be talking about vectors in 2 and 3 dimensions, and we start with vector in 2 dimensions. So, some of you more or less have heard about vectors before, so let's first do a brief review. What is a vector? Okay. The definition of vector is very simple. Before, we have numbers, which are 3 and 4 and 5. They are called scalars. Numbers. Okay. Vectors is kind of different, and that comes from when we try to represent a force, okay, or velocity, or maybe acceleration. We face trouble because this kind of quantities, they have two components. The first one is the size, or we call later the magnitude of the force. We have 20 Newton, 30 Newton, 40 Newton. Great. But even with all the 20 Newton, 40 Newton, the same kind of size of force, you do have different directions. So vectors are invented to represent something that has a length, or size, or magnitude, and a direction. So usually the way to represent it is like an arrow. You have a segment, the side tells you the magnitude or the size of the vector. A longer means bigger, and also a direction to tell you, okay, which direction it is pointing at. That is a vector. And of course you can see it's a very good representation of force, velocity, and accelerations. Not only you care about your traveling at 20 miles per hour, you care about your traveling 20 miles per hour to the east. So two quantities at the same time. All right. How do we represent a vector? Like a number, we say x equals 3. We use variables, letter to represent the variables. For vector, we use letters. But moreover, not only we use a letter, we put a small arrow on top of the arrow to indicate this is a vector. Okay, so this is a vector, vector u. It can represent an arbitrary vector. Or sometimes you have vectors in a complicated shape like this. O, C, A, B, D, E, F, whatever. So if you know where the vector starts and where the vector ends, you can simply tell people, okay, I want to talk about the vector B, which means the vector going from here all the way to here. Okay. You can also talk about vector OD, which is what's going on from here to here. So if you take it out, it's going to be something like this. So clearly you have a length, you have a direction. So if you know the starting and ending point, or initial ending points of the vector, you can simply use the same way you represent a segment, except, number one, the order matters. BE does not equal to EB, so this is slightly different from a segment, right? Segment, you exchange the starting ending points, it doesn't change a thing. This one does have a direction. And you know that because you have a small arrow on top of it, so you know it's a vector. Number 3, the magnitude. It's what we say by size, okay? So the magnitude is nothing but the length of the segment. And if we know a vector, what we do is we simply put an absolute value around it, and this indicates, okay, I'm talking about not the direction, but only the magnitude of the vector. Well, this is not something new because we have done this before. -2 equals 2. That means what? I don't care about are you bigger or less than 0. Okay. Or let's say I don't care about are you pointing to the right or the left. I just care about the size of your number, which is just +2 always. So this is a natural extension of what we had before for absolute value. And number 4 is probably the most important. That is, how do you add two vectors together? And how do you subtract two vectors together? And the rule we follow is going to be the triangle law. Some people call it parallelogram law. We'll introduce both. Triangle law. The idea is quite simple. Let's say we have a u given by this, we have a v given by this. Okay. Now what you can do is you can do u plus v. To do u plus v, what you need to do is you need to make sure they are attached from head to tail and head to tail. Okay, so where the first one ends is where the second one starts. So if you put u here and you put v here, by moving them, which doesn't change them, this will be what you have for u plus v. And clearly you can see the job is try to put both vectors into the same triangle and arrange them in a certain way. And then the third side created by this triangle will be the u plus v. All right. Similarly, for u minus v, we also put these two into the triangle, but we arrange them differently. Before, we make sure they are like starting, ending, and where the first one ends is where the second one starts. For minus, we put them and we make sure they start at the same point. So after that, this will be u minus v. Then clearly you see, well, this is confusing. Why? Because you have two choices. You can either go this way or this way. Now by convention, we will make sure that it always points to the first one. Okay. These definitions are really interesting. Why? You can think about several examples. Number one, u plus v. Okay, that's what we did. Okay, and by something we know before, somehow it should equal to v plus u, right? When we see a plus, we say exchanging the order really does matter. What is v plus u? That is, you start here, then you do this. This is what you get from u plus v. U first, v second. This is what you get from v plus u. U first, v second. V first, u second. And somehow they should be the same. Well, number one, by my drawing, they does look the same. But you cannot trust my drawing. Now, if you think about it, actually you can simply merge them to be u, v, and v, u, and you form a natural parallelogram because these two are the same, so they have the same direction. These two are parallel to each other. Meanwhile, they have the same length. Similar things for v. So from here, you can see u plus v and v plus u all point to this diagonal entries of the parallelogram. So of course, they're the same. What do you think the relationship with u minus v and v minus u? Naturally, we think you should put a negative sign on there. Right? They're not the same, but they do have the same size. Opposite direction though, but if you write it down, it's very easy to do. And you do know this is u minus v because it pointed to the first one, and you do know this is v minus u. They're exactly the same except for, because they are the same third sides in the same triangle, but they pointed to different vectors. The first one pointed to u, the second one pointed to v, so of course they are opposite to each other. So the definition actually naturally makes sense. That means a lot of things. Number one, if you have a wind coming this way, you have a velocity coming this way, somehow they merge together, you will be going in this way. And how did you do that? You actually did the triangle law. Okay, so which is different from what we had before. Because if you have 2 plus 3, you always have 5. Because they all point in the same direction. But now your 2 can be going this, your 3 can be going this. So the 2 is not completely contributing to 3. So maybe your answer is going to be a little bit less than 5. How big is it? Really depends on how big of the difference between these two directions. Sometimes 2 and 3 can even cancel each other if your 2 is going this way. Okay, so that's the beauty of vectors. And you do it by triangles. Finally, scaling. What do you mean by a number times a vector? For example, if you know this is u, what do you mean by double u? Or half u? Or even negative 3u? Okay. Now keep in mind, every time you have a number here, before a vector, you always keep the same direction, but change the size. So if you have 2u, you keep the same vector in the same direction, but double the size. Why? Because 2u is basically what we defined by u plus u. So it's the same thing as addition before. You add the same thing for multiple times, you change the size. Similarly, this one, you shrink the size. Now, negative 3u is nothing but negative 3u. You know what 3u does. 3u just triple the size. Okay? So probably the only thing you want to figure out is, what does negative mean? What does negative mean? Well, I do know one thing. That is u plus negative u should be 0 by common sense. Something, for example, 3 plus negative 3 equals 0. That's how negative 3 is defined. So you need to ask yourself, for which kind of u, for which kind of vector, if I add it, this u become nothing. That means you start from here, ends here, and then you start from here, go back here to the original point, then you will cancel yourself. Okay. From here you can see negative u should be the same vector, but in the opposite direction. So if you do addition with u and minus u, they should cancel each other. Okay. So finally, negative 3u is very easy. You just take negative u and triple it. Okay. Or you triple it first and then do a negative. Either way, you have this answer. All right. That's the basics about vectors before in geometry. Now, of course, we want to do things in a little bit careful way. So now we want to talk about vectors in a coordinate system. Remember what happened before. We have angle, we have wide angles in the woods, but then we put them in the farm and standardize them. And after that, suddenly everything becomes super clear because now every geometry can be transformed to algebra. This is called analytical geometry. Okay. We want to do the same thing for vectors. So first, we draw a coordinate system. Okay. Second, we take a vector and we want to put these vectors back into this coordinate system. How can you put it? You can put it here, 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 you can put it here. As long as you keep the length, the magnitude, and as long as you keep the direction, they're all the same. So you have so many ways of putting it, but we have a standard way of putting it. That is, it always starts from the origin. Then you only have one way, and that way is standardized. Make sure the initial point is always the origin. So you do have multiple ways of putting it, but this will be the correct way. Or not correct, let's say this will be the standard way. Okay? Just like whenever you put an angle here, you can put it in this way, you can put it in this way, but we say, hey, always align your first side with the x-axis, then you only need to worry about the terminal sides. Always align your initial point with the origin, then you only have to worry about the ending point. Same thing. Okay? After that, how do we give it a name to tell people which vector we're talking about? By the way, this time we want it to be precise. Well, we simply tell other people the ending point. Once you know where the ending points are, you also know where the initial points are. Then you will know what the vector is, right? So you only need the ending point. It's gonna be a point. But now to tell people we are not talking about a point, we're talking about a vector, we change it to angle bracket to tell people we are talking about a vector which starts from 0, 0 and pointing to xy. Okay, so let's draw several vectors. Can you draw the vector 1, 2? This is the point 1, 2, then this is the vector 1, 2. It pointed to the right, 2 units up, 1 unit to the right. Can you draw negative 1, negative 3? Okay, 1, 2, 3, 4. Negative 1, negative 3, it's here. Can you do 2, 0? Okay, and you can try several more examples. It's very easy. It's just join the points and then connect the point from the origin. That's how we tell people a vector. So not only we can tell people the name of the vector, now we can actually quantify it to tell people the exact location. Now second, of course in real life, maybe you are not so lucky. Maybe sometimes your tests have a bad behaving vectors. For example, if you have a triangle here, and somehow you want to use vector to solve some of the properties, okay? Then you know point A is 4, 1. Okay, pay attention. We used a parenthesis because it's a point, not a vector. Okay. Point B is going to be 1, 3. And point C is going to be 5, 5, I think, is working. Now I wonder, what is vector AB? Or let's say, what is this vector? Because it always starts from 0, 0. What do you think? So far, I think you already start to get a feeling of the vectors. To tell people the vector, where the vector is pointing at and how long it is, you just tell people the horizontal or the x direction, how much you should go further to the left or the right. And then you tell people how much you should go up and down. You have a horizontal and vertical component. Okay, so going from A, 4, 1, to B, 1, 3, how do you go horizontally to go from 4 and reach 1? You go to the left by 3. You will get it. How do you horizontally to go from 1 to 3? You go up by 2. You can go from 1 to 3. Okay. Now more precisely, actually what you get is actually I use 1 minus 4 because I want to start from 4 goes to 1. And I want to start goes from 1 and goes to 3. Now if you think about it, it's nothing but 1, 3 minus 4, 1. Because this is where you start. And this is where you end. So of course, how much effort should you do in which direction? You use the ending minus the starting point. So that's how we do the vectors. Starting point, actually the other way, ending point. Point minus the starting point. You start from 5, you want to go to 8, go positive 3. You start from 5, you want to go to 2, go negative 3. How do you do it? You use the ending minus the starting. So if you look at these vectors, for example, what is vector AC? Now you know to take 5, 5, that's where I want. Where do you start? You start from 4, 1. So how do you get from 4, 1 to 5, 5? Well, number 1, horizontally, I go to the right by 1 to go from 4 to 5, and then I go up by 4 to go from 1 to 5. So that's how we do it. All right, keep going. If you know V equals a vector AB, can you tell me how long V is? Just by looking at these numbers. Very easy. Vector AB means this point is AB. Now if you draw the right triangle, that means this part is A, this part is B. That's what AB means, right, from the coordinate system. Now for magnitude, basically what you're asking is, in this right triangle, how long is this side? Knowing this side to be B and this side to be A, so that's going to be square root of A squared plus B squared. According to the Pythagorean theorem, all right, so a quick example, V equals 2, 4. That means this is 2, this is 4. So how long is the absolute value or the magnitude of V? Square root of 2 squared plus 4 squared. Easy. Okay. Number 4, addition, subtraction, which still satisfies the triangle law. Okay, so let's say, how you do the vector 1, 2 plus 0, 1. Let's not do that. Let's do 1, 2 plus 3, 4. Let's draw a little bit longer. Four, 3, 1, 2, 3. Okay, 1, 2. Okay, 3, 4. Can you add them together? So what do? You take 3, 4 and make sure they are starting, ending, start, ending with head and tails attached together. Then you wonder, okay, this will be, my drawing is, let's see if I can do this. Let's do 4, 3 to make sure I can draw them more separately. Okay, otherwise they're too close to each other in terms of directions. 4, 3. Then what we do is we do head, tail. Doesn't matter which one we do first or second, so we can also start from 4, 3 to add 1, 2. But either way, this is what we have. Okay, what you wonder is, how long is this horizontally and how long is this vertically? Okay, if you combine these two vectors together. Now think about it. What you did is basically you start from a vector, you start from 0, 0, and you end up at 1, 2. And then you start from 1, 2 to go another 4 to the right, another 3 to the top, based on 1 and 2. So that's simply go to 1 first and go another 4 horizontally, and go to 2 first vertically, and then go another 3. It's nothing but simply adding them together. It's just common sense. It's almost like go east for 20 miles and then go east for another 30 miles. Then together you went 50 miles. You start from where you left, right? And you accumulate all your effort together. From here, we find if you represent a vector into a coordinate, it's super easy to do the addition. Don't worry about triangles anymore. If you have two vectors, it's simply one plus the other. Then it's not hard to see if you have minus. It's simply the horizontal minus the horizontal and the vertical minus the vertical. This is so convenient. That means whenever you have a velocity pointing to the northeast, you can decompose it into the horizontal velocity and the vertical velocity, and the horizontal ones can be calculated separately from the vertical ones. You can do them separately, and eventually when you finish, you combine them back. That's a decomposition, which is super convenient. So for example, from now on, I would say, hey, what is 1, 2, a vector, plus 0, 3, and then minus 4, 5. To do it, you should first draw 1, 2, combine it with 0, 0, 3. Okay, you got the new vector. And then you should draw 4, 5 here and draw another triangle to figure out what this final vector is. But now forget about all of them. It's simply just the final answer is going to be -3, 0. Done. You do it by triangles for multiple times, you will get the same answer. Because basically these two rules come from the triangle law. All right, that's how we do addition and subtraction. What about scalings? Like we said before, you have u, you have 3u, okay, 2u, same velocity, same philosophy. You double the size, you triple the size, you change the size. So say you already have a vector. Okay, you have the horizontal, you have the vertical. Now you want to rescale the vector to double it. Can you see that? It's the same as doubling the horizontal and doubling the vertical. So if you have a number times a vector, you simply just use the number to times the horizontal and use the number to times the vertical. So for example, if you want to do 2 times 1, 2, which you will double the size of 1, 2. According to what we draw here, you simply just double 1 horizontally, and then you double 2, which give you 2, 4. Okay, negative 3, 4, negative 2 simply equals negative 3 times 4. Negative 3 times this give you negative 12, 6. Very easy to understand, and they make sense. All right. Okay. Finally, unit vector. Why do we care about unit vector? Well, number one, unit vector is vector with length 1. So magnitude 1. Why do we care about unit vector? Think about it. That means you have a vector may have different directions. The only thing they had in common is they all share the same magnitude, which is 1. That means all of these vectors, their ending points are on a unit circle. And we have done so many trigonometries so far, I don't think I need to mention to you how important unit circle is. So that's why we care about unit vector. Moreover, if you think about it, that means we only care about the angle. We don't care about the length. Or equivalently, we only care about the direction. But we don't care too much about magnitude, so we make them standardized. This will give us all the information about the direction. All right. Number 3, unit vector I and j. There are many unit vectors. For example, if I want to give you an example, square root of 2 or square root of 2, actually all the cosine theta sine theta pair is going to give you something on the unit circle. Therefore, give you the unit vector. Okay. But we do want to focus on 2 special ones. That is I equals 1, 0, and the j equals 0, 1. That gives you the unit vector here and the unit vector here. The reason we care about them is because I stands for the direction of positive horizontal directions. Okay, and the j stands for the positive vertical direction. Therefore, any vectors which is given by x and y can be decomposed into the horizontal component plus the vertical component. Which means if you have a 2, 3, what you should really think about is this means go 2 in the horizontal direction and go 3 in the vertical direction. And if you have negative 2, 1, that basically means go negative 2 in the horizontal positive direction means going to the left. Okay, plus 1 times j. Okay, we will call this the horizontal component will call this the vertical component. Of the vector. Okay, so that's the first important thing about unit vector I and j. They give us a nice decompositions. Now number 2, sometimes you do not know the vector in terms of coordinate system, but instead we have a very familiar setup, that is the heading. Do you remember? Let's say we have a velocity. Okay, we have a velocity, 20 miles per hour towards north, 40 degree east. Okay, now the question is, find the coordinate of v as well as the horizontal and the vertical components. Technically, when we say horizontal, we mean the component in the east direction, and the vertical means in the north direction. If it's in the south, it's negative in the north direction. Okay. Now let's try to think about it. How to do it? You just want the horizontal, and you just want the vertical. Component. Do you see they're nothing but solving the right triangles, provided that this is 50 and the hypotenuse is 20. So what I will write down here is the magnitude of v is 20. Forget about the direction, okay? But then the x is going to be 20 times cosine 50 degree. And the y is going to be 20 times sine 50 degree. Okay, then the v is nothing but the x component times I plus 20 times sine 50 degree times j. So the horizontal component is here. The vertical component is here. Without a calculator, we stop here. Okay. And finally, the coordinate is going to be given by all right. Okay, so that's actually how we do the horizontal and the vertical component, which is actually a general formula. So if I'm going to write it down. Sometimes we don't know the coordinate. Instead, we know the magnitude. But then we can easily have the horizontal and vertical to be x equals v times cosine theta, y equals v dot sine theta, where theta is the angle between the x-axis, positive direction, and the direction of the vector. This actually guarantees x squared plus y squared equals v squared. That is actually the definition of the magnitude. It comes from a right triangle. All right. I know it's a lot. You do have, but they're very, very simple, even though we have a lot. So go to your webworks and try with all the elementary operations. They are pretty easy to do. Okay? Now, of course, we want to show you the application, which is why do we do all the hustle to introduce such a totally new concept Does it give us some convenience? Well, let's try to see several examples of applications. And you will see vectors are really powerful. The first one, let's see we have an airplane flying from, let's do towards. Okay, the pilot was aiming towards north, 40, east. Meanwhile, there is a wind. There was a strong wind. Oh, at 20 miles per hour, like we said. Okay. Meanwhile, there is a wind blowing northwest. Towards, let's say, towards. Yeah, from, let's do from. From the northwest. Which will affect how the airplane is going to go. It's going to push you a little bit, maybe helping, maybe going against, either way. At 6 miles per hour. Okay. So in this kind of condition, if you fly the airplane towards that direction, the question is, how fast and in which direction is the airplane actually flying? Towards. Okay, so now let's draw it. Number one, we're having an airplane. That's the best I can do. Going towards north for 20 with a 40-degree direction from the north to the east. Okay, it's flying towards that way. Meanwhile, we have a wind blowing from the northwest. If we don't say anything, it's going to be 45 degrees. So what's the result? The result will be this airplane is going to be pushed towards this direction. Okay. You want to go with 40 degrees, but definitely you go a little bit bigger than 40 degrees. The question is how big? Okay, and also how does that thing change your velocity? Does it make it faster than 20? Does it make it slower than 20? Okay, now how do we solve it? If you do things in your traditional way, there's nothing better. You need to draw the triangle. Okay, you need to solve it using the law of sine and cosine, which you know is a pain in the butt. It's so long. But this time we have vectors. And we know the total velocity, which is the actual velocity, is going to be your aimed velocity, your original velocity. Plus the wind velocity. Moreover, you know these three are just vectors. So basically what you need to do is calculate this vector, and do vector 1 plus vector 2, which we know how to do. That's horizontal plus horizontal, and the vertical plus vertical. Beautiful. Now the rest is just to get the original velocity. How do you do that? What do you know? You know north, 40 degrees west, east. And 20 miles per hour, that's where we apply the horizontal and the vertical component. Remember, we need this angle, not the 41. So this original velocity, let's call it VO. V naught. It's gonna be 20 times cosine 50 degree, 20 sine 50 degree. Okay. What about the wind? Well, the wind is coming from the northwest, But remember, we want standardized, so you start from here. Northwest basically means towards southeast with a 45-degree. Moreover, we know the length is 6 miles per hour. Therefore, the wind gives you 6 times cosine 45-degree. Pay attention, the vertical is going to be negative 6 sine 45-degree. Okay, negative. All right, with all this in mind, now what is the original wind? Let's give it a name. We call this VW, stands for the wind. So total VT total should equals V0 plus VW. But you know V0 50-degree 20 sine 50-degree plus 6 times cosine 45-degree negative 6 sine 45-degree, which is 20 cosine 50-degree plus 6 cosine 45-degree, horizontal and horizontal, vertical and vertical. Without a calculator, the best we can do is we do cosine 45 and sine 45 to be square root 2/2, and we stop there. But now let's use a calculator to actually find this number. Okay. 20 cosine 50-degree plus 6 cosine 45-degree. And that is going to be 17.1. Oh, that's an exact number. That's interesting. Okay. And then we have 20 sine 50-degree minus 6 sine 45-degree. That will give you 11.08. Okay, so that would be the final direction. What is it? That's going to be, well, some vector going this way. The horizontal is this, and the vertical is this. So from here you can see the original one was going northeast. This one is also going towards northeast, but a little bit towards east, because you have something blowing from northwest. That's the final vector. But remember what we want. We want which direction and how fast. So we want to tell people 20 miles per hour, 30 miles per hour. And you can see basically we're asking, number one, how fast means how long is the magnitude. That's going to be the magnitude of this, which is square root 17.1 square plus 11.02 square, which is 17.1 square. Which is 20.38. What do you know? It's faster than 20. So the wind is helping a little bit. Okay, miles per hour. Direction? Well, certainly we know it's northeast. We just don't know this number. And what is that number? That number should be this angle. Okay, so what can we do? We can do the right triangle and figure out this, and then use 90 degree to minus that. So the angle here is going to be 90 degree minus tangent inverse. So everything we did before for solving triangles is helping with what we have right now. that gives us 89 degree. Okay. They're definitely confused with reading and degree. So let me do the degree first. It's 90 degree minus 33 degree. Therefore, this is going to be 57 degree. Okay, remember what we had before? You had 40. Originally, you had 40. Okay, now you have a wind coming from this way. Now you have 40 and you're traveling at 20. But now you have 57. So this thing did push you a lot, actually 17 degrees more towards the east. And you're traveling a little bit faster. We didn't solve any right triangles or general triangles. We didn't use the law of sine cosine. All we did is we identified several vectors and we did each individual vectors one by one, which is nothing but just doing right triangles. Right? After that, we summed them together. We didn't worry about the triangle law. We just used the algebraic law that is horizontal with horizontal, vertical with vertical. But once you finish that, you got a nice final vector. The rest is try to write the information you want from this nice vector. This is so convenient. All right. Another example. I can still let you to feel a little bit about like why this is great. Remember, there was one example we did in the law of cosine. That is, originally there was a pilot. He was supposed to drive here for 300 miles. Okay, fly there with a 40 degree. But at first he made a mistake. He drove east for 100 degree and then he realized, crap, I was in the wrong direction. Now I want to change. So let's see. This should be airport A, this should be airport B. They're 300 miles away from each other. Great. But then I did a mistake. I drove east for 100 miles. East. But then I realized my mistake. I want to correct it. So now I want to actually go here. The question is, number one, how far are you? Let's call this C. The original question was how far are you from the airport? Let's just say like find. Let's just change it to find BC. Okay. And number B, which direction should I go? So find the direction. Which is from C to B. Can you translate that thing into vectors? Yes. Find the direction of CB. Similarly, this one actually is the size of BC, or we can change it to be the size of CB, since we're going to do CB either way. Okay, so this is some old problems we had before, and remember what we did. We calculate this is 50. Then we say this is SAS case. We use the law of cosine to figure out how long this is. Remember? Then we use the law of sine to find how big this angle is and start to tell people, okay, which direction should you go? Which is very long. But now let's do the same problem. You can actually go back to that section. I think it's 5.6. Should be 5.6. Try to see the example and compare them side by side and try to see vector is better. Okay? Now let's solve it using vectors. The key is find CB. The rest is try to find the magnitude and direction of CB, which is easy. So find CB first. But how do you find CB? Well, CB is a vector. You can simply find C and then minus B. And that would work. Okay, so points minus the points, ending minus, take it back. Point B minus point C, ending minus starting. Now what is C? C is easy. C is 100, 0. You go to east for 100 miles. Great. B? Well, let's do the math. B is here. What we know is this is 300 and this is 50. So B, is going to be 300 cosine 50. 300 sine 50. Okay. What is b minus c? That's the vector you're looking for. 300 cosine 50 degree minus 100. 300 sine 50 degree minus 0. And it's not hard to do with the calculator, so let's do it. $193. Hold on, 93, because I need to minus 100. 300 times sine 50 degree. That's 229. Okay, that's your CB, which is the red line. Okay. Now what do you know? You know this is 93. And this is 229. So question, how far are you from C and B? This, which is square root of negative 3 squared plus 229 squared. Which is 247. Okay, which direction? Well, you need to ask yourself, you know this is 229, you know this is 93. What you want is this angle. But of course, like we said before, we can find this angle using tangent inverse and use 90 minus that. So direction. North, east. The angle in the middle is going to be 90 degree minus tangent inverse. 229 over 93. $93 or 92? 93. Which is 90 degree minus 68 degree, which gives you 22 degree. So this is what we have from using vector. The whole process just involving write down vectors, write down points, doing the formulas for magnitude, for horizontal and vertical component, compared to what we had before, where we have to do the law of cosine and sine for multiple times. This is way better. All right, I think we had enough examples in class. Now try to do the web works. You will see, okay, you have a boat rolling this way, and you have a water flowing this way. Okay. Moreover, you can have actually a wind blowing this way at the same time. So you're rowing a boat, the water is flowing in one way, the wind is going in the other way. You have three vectors, but which way are you actually going? Simply just add all the three vectors. You do it with triangles, it's going to be super complicated because you have two different triangles involved. But if you do vector, adding 2 vectors, adding 3 vectors, adding 10 vectors is nothing but putting all the horizontal together, all the vertical together. It's super easy. Okay. You can also think about if you're actually rolling this way, this is blowing this way, and this is blowing this way. Which way should you actually change the direction you roll in order to go straight? You will see all kinds of problems like this in the examples in the web work and the textbook problem. Try to do them. Vector is not a hard concept, but if it's new to you, take your time, do some exercise. it will be definitely worth it, because it becomes super easy to talk about velocities, force, and accelerations in physics after we know vectors. Okay. Before, the only tool we have is triangle, which is nice, but meanwhile, it's not flexible enough, it's not easy enough, especially when you have more than two forces. Okay, then you have to have multiple triangles.